doing needs to use this, right? I don't think that even happened in the onto, did it? Right. But so what he does now is I think he looks at, in my notation, F1 composed with F2 inverse, is it? Is it a composition or is this a joining of paths? It's a path join, right? It's not composition. So you're saying path 1 join path 2 inverse. So like we're up, here's a picture. We're at E. F1 does what? F1 goes up here. It goes up here to F1 of 1, whatever that is. We didn't even name yet this point, right? And then F2 inverse starts at the terminal point of F2 and goes back to where it starts, right? So F2 inverse is this guy. So that's a loop. That's a loop at E. But what can we do to loops in a simply connected space? Right, we can contract them to a constant point, which means that F1, F2 inverse is equal to E. Well, that's not true, but homotopic, right? And that implies that
there's also a homotopy of the corresponding path in X that builds their start.
Yeah, and then you take this homotopy and project it down through the covering map. Yeah. And then that makes these equal, which is the injective. I've written enough. I think I've written enough about that on the board. I just, yeah. Now, So guys, the corollary to that, corollary 5.5, try to wrap this section up so we can excuse me, reap the benefits next time. So the corollary 5.5, it says what? It says if we have a covering map and E is simply connected, I'm trying to think of how to put this into words. See, this is what I get for grading today. I should have taken that time and prepared for class. Don't you think? Emily's like, you didn't really grade. Emily's like, you didn't really grade though either. So what were you doing? I did try. Let's see here. Covering map and E simply connected. For each point, Y in the fiber over P, over X not rather, let alpha Y be path from E to Y in E and gamma sub y equal to covering map P composed with alpha of y be the loop in X based at B. Based at X naught. If gamma is any loop in X based at X naught, then there exists unique loop gamma sub y such that gamma is homotopic to gamma y with endpoints fixed. So what is this saying? Can you guys put it into words for me? Since I'm having trouble with words today. It's what? Yeah, I think this is just a restatement of what we've been saying, which is that if you take two things in a, to complete my picture, if you take two things, the thing I never drew in my initial picture, you want to look over here, Jonathan. To complete the picture, I think what we've done, right, is the homotopic path to the, maybe I should do it in purple to be stupidly color coded, right? The purple path is something like that, So all of the loops that are homotopic, they lift to a class of paths up here which are homotopic and have the same initial and terminal point. So, and this is saying that that's everything. There's nothing escapes. This completely characterizes the possible homotopic loops. Let's see here. So finally getting to the point, getting back to our initial application that we started with this week, right? He says, well, if you look at the covering map from the n sphere to projective n space, right? He says if E is the north pole of Sn, right? And let x naught equal to P of E, he says then P inverse of x naught consists of what? 2 points, right? So what does that say the fundamental group of Pn is? Oh, by the way, Sn is simply connected. So theorem applies. You have proved that in exercise 3.1. Yeah, it's in exercises. So knowing that Sn is simply connected, all right, for n greater than or equal to 2, that implies then, because, by the way, I know for those of you, it's just you, right? You're not the group theorist. Not yet.
I mean, I know what a group is.
You know what a group is. So one of the first things, well, early on in group theory, we learned that if you got a group with 2 things in it, then up to isomorphism, you know what it is. It's just Z mod 2 or a cyclic group of order 2. You could think about it as 1 and minus 1 in the integers, if you like. What's that? What's what? Oh, it was like Z mod 2Z. It's got 2 equivalence classes, 0 and 1, so to speak. 1 plus 1 is 0 in this system. But the fundamental group of Pn is Z2. For n greater than or equal to 2. Pi 1, I should say. Higher pi's are discussed in the next chapter. And then we're out of time at the moment, but then he defines the, he talks a little bit more about the, looking at loops based on S1. I think I mentioned last time already that 2 loops are homotopic if and only if they have the same winding number, and he calls that the index of alpha, where alpha is a loop around a loop around the circle. It's the number of times that alpha circles the circle. And so he points out anyway that, of course, and I think you can already see this from my pictures, right? That pi 1 of the circle is just what? It's the integers, right? Because that's how many, that's the fiber. We have the fiber is countably many things. I suppose we haven't quite proved, well, that's what the theorem 5.6 shows, is it shows that indeed it has the requisite group structure that you need to be the integers. So maybe we'll start next time with that. But past that, of course, we have some applications of the index. Yeah, so starting with the index next time is a good move, because then we look at applications of the index, and hopefully I'll try to wrap up as much as I can in terms of applications here. So if I do my job, we'll get through vector fields next time. I just have to be, prepared not to prove things that will eat all our time. But I have no regrets. I'm happy with what we've done in here. So I'm particularly happy with that picture. Thanks, guys.